I will be talking about mainly my PhD work at Ohio State, and which is primarily focused on developing genetic marker outfits and genetic markers to discriminate among different spawning stocks in Lake Erie West Basin. So the purpose is to hope to use this marker to understand how different spawning stocks contribute to the lake-wide population. So first, I would like to acknowledge our funding agencies and collaborators. Our main funding source has been come from Sport Fish Restoration Act dollars, which is administered by Ohio DNR. And we also have additional fundings from Lake Erie Protection Fund, as well as Ohio Sea Grant. And I would also like to thank several agencies here and other collaborators to help us collect samples. So today I will start with talking a little bit about walleye spawning migration and the importance of knowing stock structure and quantifying the spawning stock contribution to fishery. And this will set our research questions about the stock structure and the spawning stock contribution. And then I will also introduce the method, the markers that we have developed, and show you the result of using these markers to answer our questions and to better understand the stock structure and their contribution. And finally, I will finish up the talk with a summary and some management implications. So we know during the spawning season, this adult walleye will migrate to discrete rivers around the lake and reefs on West Basin to spawn. And among these walleye spawning stocks, these three spawning stocks, including Ohio Reef, Sandusky River, and Maumee River stock, are known as the largest three spawning stocks in Lake Erie. So our study has been focused on these three stocks. So there are two questions important to the fishery management. So the first question is, do local spawning stocks show stock structure? So how do we know if this stock has structure? So from behavioral perspectives, we can see how many adults return to their natal site or stray to other site to spawn. So if these adult fish tend to return to their natal site to spawn, then it would increase the reproductive isolation among these spawning stocks, so making them become an independent stock. And then we might see some stock structure. And if this adult fish has a tendency to stray to non-natal site to spawn, to go to a random site to spawn, then it would increase the connectivity among these spawning stocks. And we might see less or no structure among these spawning stocks. So answers to this question will help us determine whether we should manage them as multiple stocks or just a single stock. So the second question is, how much does each spawning stock contribute to the lake-wide population? So here I'm going to use a hypothetical example to explain why understanding the stock contribution is important. So assuming these four spawning stock has equal contribution, and if in a certain year one stock didn't do very well, such as suffering some high mortality, then other three stocks might compensate the overall recruitment. On the other hand, if they contribute disproportionately, say the Maumee River has the greatest contribution, and if it didn't do well in a certain year, then we might see a significant drop of the recruitment in that year class. So understanding the stock contribution, whether one stock has greater contribution than the other, or how this stock contribution change across time and space, will provide some information that can benefit management. And maybe also help to answer why we see such a fluctuation of the population. So our research goal is seeking to identify markers that can discriminate among these local spawning stocks to answer the questions. So first we explore the spawning stock structure by identifying the natal origins of spawners and to see if they have natal homing behavior. And second, we quantify the stock's contribution by identifying natal origins of juveniles recruits that capture in the open lake to understand their stock contribution. So we have been trying to use all this microchemistry and genetic marker to understand the stock structure and their contribution. So next we will see the evaluation of using strontium as a stock discrimination marker in larvae. And then we will use strontium to determine the natal origin, of spawner to see if they have a natal homing behavior. And then we will also show some result of genetics, so see if genetic marker can help us discriminate among the spawning stocks. And lastly, we will see the result of determining natal origins of juveniles collected from the West Basin to understand their stock contribution. So let's start with the otoliths. So otoliths are cellular stones in inner ear of fish. So they can help fish hearing and balance in water. So these are just some pictures showing the otoliths extracting from the fish. And the bottom right is the pair of otoliths. So otoliths will grow with fish age. And so they, just like the tree rings, they will form the daily or yearly ring structure. So if you put it under microscope, we can use otoliths to age fish or estimate the fish growth rate. And in addition to that, otoliths also incorporate metals or some trace elements from ambient water. So we can measure the elemental composition in otoliths to determine their natal origin or trace their life history. So here I'm using otolith strontium as an example to see how we can use otolith strontium to determine fish natal origin. So assuming the larval fish were born in different rivers, say river A has a higher water strontium and the river B has low water strontium. And so this strontium element will deposit in otoliths in different proportion between the two rivers. And then later on, we can extract the otoliths from the adult or juvenile fish and measure the elemental concentration in the otolith cores. And then, so for example, if we have a high otolith, one individual has a high otolith core strontium, then we can infer that the fish likely originate from the river A. So the prerequisite of using otolith chemistry to determine the natal origin is there must be some water chemistry difference. So if the water chemistry differs among our three spawning locations, then we can use this otolith chemistry as a natural tag to determine the natal origin or discriminate among the stocks. So here's the water chemistry data. Here we show the water strontium calcium ratio among our three spawning locations. So as you can see, the water strontium level is consistently higher in the Sandusky River than the Maumee River and the reefs. And although the Maumee River also has slightly higher water strontium than the reefs, but the difference is not so huge. And there's also a concern about the Maumee River plume could cover the whole reef area, and it would make the water chemistry very similar or even identical between the reef and the Maumee River. So we couldn't really use otolith strontium to discriminate between the reef and the Maumee River fish. So here we basically focus on using otolith strontium to distinguish the Sandusky River fish from the other two stocks. So similar to the water chemistry, this is the otolith strontium of larvae collected from the Sandusky River and the Maumee River. So as you can see, we have across these 7 years data, the Sandusky River larvae is consistently have higher otolith strontium than the Maumee River larvae. Despite some interannual variation, we have a low year in 2011. So if that's a concern about using this interannual variation could confound our spatial interpretation, then we can create an annual library data of using this larval otolith strontium and then use that as a reference to determine the adult or juvenile natal region for a specific year class. And for those data that we don't have larval otoliths, we can instead use this logistic regression model built based on the previous larval otolith data with multiple years combined. So the idea is that we can measure the otolith core strontium and using that formula to estimate the probability of fish natal region. For example, if you have higher otolith strontium, and then you get a higher probability of fish originating from the Sandusky River. And if you have a lower otolith strontium, then you have higher probability of fish originating from the Maumee River. Or it could be from other sites, other location that has low water strontium. So we learned that the otolith strontium can be used to discriminate between the Sandusky River and the Maumee River. So now we're going to use the otolith strontium to determine natal region of spawners to infer their stock structure. So we processed 167 spawners collect across the spawning season, and during 2012 and 13, and there are sample size for each spawning location or for each stock. And again, we measure the otolith strontium concentration in these spawners' otolith cores. So if we have high strontium in the otolith cores, then we can determine that the spawners originating from the Sandusky River. If it has low strontium, then we can determine the spawner originate from the Maumee River. So here's the overall result of otolith core strontium of the spawners among these three spawning sites. So as you can see, the fish, the yellow boxes there, the spawners collect in the Sandusky River has much higher otolith core strontium than the Maumee River and the reef spawners. So this indicating that if not all, at least a large proportion of the Sandusky River spawners likely originate from Sandusky River, so showing their strong natal homing behavior. And although we couldn't really use otolith strontium to discriminate between the reef and the Maumee spawners, but we didn't find any fish spawners collect in the Maumee River or reefs have Sandusky River signature. So this suggests that Sandusky River-born fish, at least from our sample, we didn't find any Sandusky River-born fish straight to Maumee River or reef to spawn. And using the logistic regression model, we can estimate the natal homing rate. So up to 98% of the Sandusky River spawners show natal homing behavior. And up to 98% of the Maumee River or reef spawner also show natal homing behavior. But we couldn't use otolith strontium to distinguish between the Maumee and the reef because there's strontium similarity. So is there any evidence of straying behavior? So if we use the fish age and compare the otolith strontium within each year class, so you can see within each year class, the otolith strontium, the Sandusky River spawner always have higher otolith core strontium than the Maumee River or reef spawners, except one individual that we found in year class 2008. That's a 5-year-old female collect in the Sandusky River, but has relatively low otolith core strontium. So it's even similar to the Maumee River signature. So it might be a Maumee River-born fish, but straight to Sandusky River to spawn. So next we are going to see if we can use genetic marker to discriminate among these three stocks. So the idea of using genetic markers is that if adults, they don't stray among the spawning stocks, so making some reproductive isolation, that we might see some genetic difference among these spawning stocks. So then we can use this genetic difference to discriminate them. So especially we want to see if we can discriminate between the reef and the Maumee, since we can't really use otoliths to tell them apart. So we use next generation sequencing approach to evaluate the use of single nucleotide polymorphism, or SNPs, as a stock discrimination marker. And the advantage of using this approach is compared with previous microsatellite studies, usually using 10 or 20 loci, this method allows us to obtain thousands of loci across the genome. So it will increase it can increase the chance of identifying some highly differentiated loci that can be used for star discrimination. So then we processed 370 spawners across the spawning season during 2012 and 13. And here's a sample size for each stock. So in addition to the 3 western stocks, we also include some samples from the Detroit River and the Van Buren Bay. So and after lots of bench work, sequencing, and computing, we will be able to get 3,000-ish SNP loci in all the samples. And we ran a lot of genetic analysis, but here I'm just going to show you a couple of most important findings we have. So the first is, unfortunately, with such a number of loci, the loci discrimination ability was still very low. So we were using cross-validation assignment tests to see how many test samples can be correctly assigned and assigned back to their stocks. So we are testing 3 stocks here. So if the loci cannot do any, if the loci don't have any discrimination ability, it should give us 33% correct assignment rate, which means by random or by chance, one third of the test samples will be correctly assigned. But our correct assignment rate just above this null level. So this indicating the genetic loci we have has some discrimination ability, but it's just too low to be useful. So there's a statistic phenomenon showing that the significance of low divergence data set can be detected by increasing the sample size. So then we trying to figure out how many samples we need in order to get a good assignment result. So then we ran a simulation data for 2 populations in which we try to maintain the low divergence, the low diversity of the population, just like the walleye data we have, but we try to sample varying number of individuals per stock and number of loci. So with increasing number of sample size, we found, and we using this data set to perform the assignment test, and we found when the sample size up to 600 individual per stock and 12,000 loci, the correct assignment rate can be up to 75 or to 90%. So this kind of give us an idea how many samples we need in order to get a good assignment by using this genomic data. Okay, so since we can't really use the genetic data we have to perform the assignment test or discriminate among the stock, so right now we just use orthostrontium to determine the natural regions of the juvenile fish to see which stock contribute to the lake-wide population. So we processed 222 juveniles collect from across the West Basin during summer for the 3 years. And so there's a sample size for each year. And again, we measure the orthostrontium in juveniles orthoid core to determine their natural region. And this is the histogram, shows the number of juveniles with varying orthoid core strontium. So as you can see the plot on the right here, that we have few individuals, juveniles that has relatively high orthoid core strontium, so indicating they come from Sandusky River. And if we split data by collection year, and we found there are 5 Sandusky River fish collected in 2011 and 1 from 2013. And of course, we can also use logistic regression model that I just showed you to determine their natural region. But since we already have the larval orthoids data for these years, and we want to match the larval orthoids data with these juvenile fish to determine their natural region more precisely. So just make the plot wider. And so here's the range of orthostrontium of 2011 Sandusky River larvae. So we found about 9 or 21% of the juveniles likely originate from the Sandusky River. And here's the orthostrontium of Maumee River larvae, and we found 34 or 79% of juveniles from the Maumee River. And we didn't find any juvenile that has orthostrontium lower than the Maumee River larvae. And we did the same thing for the 2012 and 13 collection. So as you can see, the range of these larval orthos strontium slightly vary from year to year. So this indicating the interannual variation exists. But we also found that quite a few number of the juveniles that orthostrontium has even lower than the Maumee River larvae. So this fish might come from Reef or Detroit River, because we know these two locations could even have lower water strontium. Okay. So overall, we see the stock composition differs among these 3 years. So this indicating the stock contribution might vary from year to year. Okay, so lastly, the summary and implication. So our finding shows the stock discrimination is possible but not perfect, and the orthostrontium can be used to discriminate Sandusky River fish from other stocks, but not for the Maumee River and the Reef. And using the genetics, we found the 3 stocks are weakly differentiated, but with existing sample size, we couldn't really use the genetic loci to reliably discriminate among the stocks. And from the simulation, we learned that the increasing sample size could improve the loci discrimination ability to a useful level. And we also found some evidence of stock structure. Despite weak genetic differentiation, we found evidence for stock-specific reproductive behavior. So it looks like these spawning stock have strong native homing behavior, so it could make them reproductive isolation. And from the orthos chemistry, we found a high native homing rate of these spawners at up to 98%. And ultimately, this result suggests that Western Basin stocks should be managed independently. And further tagging studies would help better understand this phenomenon, as well as stock-specific migration rates and habitat use during the non-spawning periods. So from the juvenile chemistry result, we found the relative stock contribution could vary from year to year. And the contribution of the Maumee River and the Reef stocks appear to be very high during these weak recruitment years. However, the relative contribution from these 2 spawning stocks remains unknown, so owing to unsatisfactory markers. So similar studies during the strong recruitment years will be done this year, and so that we can verify our previous findings. And we didn't find many juveniles originate from the Sandusky River in West Basin. And this makes sense because we know there's a hydrodynamic model shows the water circulation pattern that can carry the larvae directly to Central or East Basin. So we need to further determine whether the Sandusky River fish are directly contributing to the Central and East Basin recruitment. And finally, developing orthos microchemical and genetic signatures from Central and Eastern Basin stocks could help discern other spawning stocks. Okay, with that, I would like to take questions if we have time.